Today we're starting chapter 13, which is all about measurement. So this class is called Geometry and Measurement. This whole chapter, which is a little longer than the chapters that we've done so far, it's got 5 sections in it, is all about measurement and converting between measurement systems. Today we're going to be talking about linear measurement. The word linear refers to measuring in a straight line, like you would with a ruler. Okay, so we're measuring a distance specifically in a straight line fashion. Remember that distance is never negative. I just graded a college algebra test where somebody told me a distance was negative. I don't think they understood they were really finding distance is the problem, but they were. The distance between A and B is the same as the distance between B and A. Okay, so it doesn't matter where you start and where you end, the distance between them is the same. And we have 2 primary measurement systems, English, which is what we're going to be focusing mostly on today, and metric, which we talked about last time. The linear measurements that we're going to be using today, as we start anyway, are the following. So we have feet or foot, yards, and miles. There are 12 inches in a foot, 3 feet in a yard, and you can either do 1760 yards in a mile or 5280 feet in a mile. Now, I mentioned last time that I worked a lot with my kids about this time a year ago, quarantine time, on conversion with English units. And I'm going to show you something that I had seen before. I never really teach it this way, but I will promise you that it was the only thing that worked for my children at all. And so I think that makes it's probably worth repeating for you guys, since some of you will be working with kids that might be similar to my own. So we're going to take a look at conversions. And what I'm going to show you in terms of my conversions, my husband thought I was crazy, by the way, when I told my kids this. He's like, why don't you just? And I was like, because it's not working. That's why I don't just. So we're going to start with whatever units they give us and whatever measurements. So we've got 72 feet. And we're going to make a fence. So if you ask my kids to this day, they might have forgotten some of this, but this is what they call the fence method. Okay, it doesn't really look like a fence. It kind of looks like a chart of a horizontal line and a bunch of vertical lines potentially. The question asks us to change the feet into yards. So, in order to get the feet here to go away, I have to have a measurement of feet on the bottom so that they will cancel out. Okay? So they're always along a diagonal from one another if I'm wanting something to cancel out. The other thing then is that if I have a conversion that relates the 2 items directly together, then I'm able to use it. And I do on this one, right? I have a conversion that relates feet to yards, which is what I've desired to have, so I can put yards on top. So this will be just a 1-step conversion because I have a direct relationship between these 2. If I wanted to do inches into yards, typically speaking, your kids are not going to be able to make the jump to go straight there, and you'll have to have a couple of steps. We'll get there in a moment. We need the relationship between feet and yards to be the numbers present between, or beside, rather, the yards and the feet. So it says 3 feet is equal to 1 yard. Now, I want to talk about why we're able to do this and what's really going on behind the scenes of why this works. Because undoubtedly some child's going to want to know. My kids didn't care. I mean, I told them anyway, but they didn't care the why. But some kid's going to want to know why. You had those kids in your class? Like, as a student, have you had those kids in your class? I have. So there is a good reason for why this is working. And the reason that we're able to do this is because this is equivalent to multiplying by a fraction. The fraction is 1 yard on top, 3 feet on bottom. And the reason I'm allowed to do that is because the value on top and the value on bottom are equal. So you're always able to multiply by the number 1, right? Because it doesn't change the value of anything. Well, it doesn't look like this is the number 1, but they're equal to one another, so this is equivalent to the number 1. Crazy, right? But that's the way it works. So what are you going to do then? Well, you would multiply across the top, you multiply across the bottom, you divide. Or if you want to simplify across diagonals, you can do that too. So this one actually simplifies very nicely across the diagonal, but it's equivalent to doing it the same either way. If I multiply across the top, I have 72. Across the bottom, I have 3. What's 72 divided by 3? 24. So this is 24. And the units that I'm left with are the units at the end that are on top, yards, because everything else canceled out. So this is 24 yards. Now, real life data does not always have to give us whole numbers, so let's check out the second problem. I'm taking 8923, and it's in yards, and I want to turn it into miles. So in order to get the yards to cancel out, I have to have yards on bottom, and I do have a direct relationship on the previous slide over here that connects yards to miles, right? So I can put the miles straight away on top, and I can notice and mark out if I'd like that the yards are can cancel. Now that chart, it's directly above it in your notes, actually shows that you have 1 mile equivalent to 1,760 yards. So I have 8923 divided by 1760. It is not a nice whole value. We'll go to 2 decimal places. What did you get? What was it? 5.07 sounds good. And it is in miles. You might look at 1 and 2 and say, well, why are those set up differently? Just because there are different ways you can ask the same thing, that's all. I could have used all the verbiage the same way I did on problem number 1 and problem number 2, and then you'd have to write the word miles down. If it's written already for you, that's fine. If it's not, you need to make sure you write the answer in that unit, okay? Okay, next one's a little more interesting. Ready to give it a try? This one starts out as 37 miles. I'm going to start over here because I'm going to need a little bit more space. And I want to turn it into inches. So regardless of exactly what you do next, miles has to go on bottom. That's a true statement. But as you're looking back on that chart, you do not have a miles to feet or a miles to inches relationship, right? You can go in miles to yards, or you can do miles to feet. And you can kind of pick which one you want to do. One way works a little bit more quickly. The other one still works. So do you want to turn miles into feet or miles into yards? What'd you say? To feet. I think that's our fastest way to go. So our miles are canceling. Use yellow next time. And what's the relationship? How many feet, how many miles? Where do I put my numbers?
5,280 feet is in 1 mile.
Exactly. Good job, Elizabeth. So 5,280 feet is in 1 mile. But I'm not done, because it didn't have the problem ask me to turn things into feet. It asked me to turn them into inches. But I'm closer than I was before, because there was a relationship between feet and miles, and I actually have also in my table a relationship between feet and inches, right? And it's probably one you knew already. So feet has to go on bottom, otherwise these wouldn't cancel. And my inches can go on top. What is the relationship between feet and inches? 12 inches is 1 foot, right? This one's actually really nice because it's only got the number 1 on bottom. I'm not going to have to do any dividing. The number is going to be a large number, though. So we need the numbers 37, 52, 80, and 12 all multiplied together. Does Somebody tell me what you get. I'll start you out. It's a 2 first.
2,345,343.53.
Shouldn't be getting a decimal if I'm only multiplying. Might have hit a button wrong somewhere in there. Try again. Somebody else have it?
44,320.
Okay, that's what I have written down, so that sounds good. This is in inches because inches are what my last unit is right here. So if I were filling it in the blank spot, this would be 2,344,320. If we had gone to yards first, we would just have to do it another time because we would have had miles into yards, and then yards into feet, and then feet into inches. Okay, so let's look at the metric system a little bit more fully. We talked about this in generalities last time. We're going to talk more specifics today from your book's perspective anyway. The metric system is an international measurement. It's used especially in science and industry. It uses multiples or fractions base units that are given by powers of 10. Everything's in powers of 10. The prefixes correspond to various multiples and fractions for all types of units. So we've seen some of these tables or similar tables to these from our last class session. But this is one. These are the metric prefixes. Kilo is K, and it represents a factor of 1,000. That's 10 to the third. That's why it's a power of 10 is what we were talking about before. Hecto, or H, as its symbol, is a factor of 100, which is 10 squared. Deca, if you'll remember we talked about deca last time, is DA. And it's a base, or a power, excuse me, I'm not using the right word, a factor of 10. Our base unit does not have any prefix because it's the base unit. So for what we're working with right now, we're working with meters as our base unit. So its factor is 1. And then the factors that go on the other side of it and get things into smaller sizes are deci is a D, and it's a factor of 0.1 or 1/10. Centi is prefix of C, and it has a factor of 1/100th. And milli is an M, and it has a factor of 1/1000th. The ones that are starred here are the ones that we use the most. It's not that the other ones don't exist, they just aren't used frequently, right? So, for example, kilograms. We use kilograms. You may not use kilograms, but many countries measure weight in kilograms. In fact, I gave a test the other day where I talked about weight in a problem and I forgot to put the unit of measure. Nobody who was born and raised in America had any problem understanding that I meant pounds. That's what I meant because I'm an American and that's how I think. The one kid that came up and asked me the question was somebody who's an international student, is this in pounds or kilograms? Because that's not his unit of measure that he thinks about, right? He thinks about kilograms. Centimeters, centiliters. In particular, milli is milliliters. So you'll see bottles measured in milliliters. So I've got a can up here right now. It's 12 fluid ounces. But right underneath it, it puts it in metric, 355 milliliters. So you see milliliters listed on a lot of your liquid pieces of equipment that you buy, or not equipment, but products that you buy. In particular, if we're working for metric, another kilo we see used a lot is kilometers. We measure races. I mentioned that last time. A lot of times races are measured in kilometers. So if you hear somebody say they ran a 5K, it's a 5-kilometer race. 10Ks, things like that. Centimeters and millimeters. What I'd like for you to take away from our chapter here that we're doing together is a basic idea that when somebody says a measurement in metric, you have some basic picture in your mind of how big that quantity is. So that if somebody says that they are 100 centimeters tall, does that make sense? If somebody says that they ran an 80-kilometer race, is that reasonable? Maybe it is, maybe it isn't, depending on the person, but maybe it is and maybe it isn't based on the measurement too, right? So there are some really nice picture measurements that you have in your notes. 1 kilometer is approximately 9 football fields, including end zones. It's a little more than half a mile as well. So you have in your mind, we think in terms of miles, right? We do. So that's another one. 1 meter, if you hold out your arm, is approximately the distance from one shoulder to the other fingertip. Another 1 meter measurement that you guys encountered last time, or it was nearly 1 meter, was the doorknob handle down. Do you remember doing that? It wasn't exactly 100 centimeters. That's what you actually measured. It's like 95 or 98 or something like that. But it was almost 100 centimeters, which is a meter. So from your doorknobs down is about a meter. A centimeter is your fingertip. Okay, the width of your fingertip, fingernail of your fingertip, whatever. A millimeter is the little pointy part on a paper clip. All of y'all use paper clips. I had like 50 paper clips in my bag this weekend because of all the papers I had from everybody's tests and stuff. So those are good visual estimations to keep in mind. Now, what we're doing on the next examples should feel like, well, we already did this, and we did. You guys did it in your activity last time, so it really shouldn't be brand new information. But what we did, if you'll remember, is that we wrote down kilo, hecta, deca. Here's my base unit, which for us right now is in meters. So let me just write meters in because we're looking at linear measurements. And then deci, centi. I'm going to use my capitals on everything. Deci, centi, and milli. So we had this idea. In fact, I'm going to put this really large on the bottom. And we talked about how we can move this, move our value left and right, and it moves the decimal points left and right. So if we're starting with kilometers, 1.68, we can literally put 1.68 in the kilometer column. And we can know that we're trying to get over here into the meters column. And we can physically move it one step at a time if we need to, so that we can see how that decimal point is moving. So when I do the 1.68 and it switches over, it'll now be 16.8. And if it moves again, now it's 168. And if it moves one more time, I have 1,680. So the decimal point is moving 1 each time. Right? I didn't move it that last time. That was it. So my number of meters is 1,680. My sixth graders, they were between the 5th and 6th grade at that point, really struggled with doing this and just counting and doing it. They wanted to see it move across in a table. So you may have kids who are very visual like that and want to see that too. Let me do the next one in a different way where we're actually not physically moving it on the table, but we're doing the same idea. So the next one actually gives me 973 millimeters. So here's my 973 if you think about where I am. And it wants me to give my answer in meters when I'm done, right? So if you count, we're going to change it through 1, 2, 3 locations. So my 973, which has a decimal point right here, will have the decimal point move 1, 2, and 3 times. So the decimal point will land right before the 9, and I have 0.973 meters, almost 1 meter. Right, that's almost the number 1. Doesn't matter to me whether you actually physically do it the way I did the first one on problem 4, or whether you just count it over the way I did on problem 5. Don't care. Just know that those are two sort of they're very related, obviously, but they're different physical ways of doing the same thing. The last one on this slide is 0.42 kilometers. So we have 0.42, and it wants me to turn it into centimeters. So centimeters is way over here. I'm going to count like I did on the last one, but if you would like to move them one step at a time, you're certainly welcome to. I need to go 1, 2, 3, 4, 4, and 5 decimal points to the right, because it's 5 places to the right in the number system. So my value starts out, I'll put the number up here, as 0.42. Here's 2 moves right there, and I've got 42. But I need 3 more, so I need 3 zeros to allow me the space to move it 1, 2, and 3 more times. So my decimal point will end here, which means I now have, I'll write it above it, I keep running out of space, I'm sorry, 42,000 centimeters. Any questions on that? I know we've already done that, but I didn't talk about it in this way. Yep,
On
Emma?
the test, are you going to allow us to do it like this, or are we going to need to set up the...
Either way is fine with me. Does not matter. Yep. Okay, let's look at a few other things in this linear measure section. The next topic is called the triangle inequality. This says that the sum of the measure of any 2 sides of a triangle must be greater than the measure of the third side. This is directly related to the idea that the shortest distance between 2 points is a straight line. Phrase you've heard forever, right? Shortest distance between 2 points is a straight line. So imagine you have these 2 points, so I can explain what this is actually saying. The shortest distance between them is a straight line, which means that any other path that I take, and I'm just going to do a 2-legged path because that creates a triangle, must have the ability that if I add these 2 pieces together, they're more than the straight line I already got. Does that make sense? So if they were shorter, then what I would actually be having, right, if they'd added together to something smaller, is that I would never actually arrive at the other point. Right, if I take this and I take this and it's actually less than the line that connected them directly already, there is no triangle. So when I'm looking at different numbers and trying to decide if they can be the sides of a triangle, what I'm trying to see is if the 2 shorter values, the 2 smaller values, are actually bigger than the other third side. Okay, I always take the 2 smallest values and I add them together. Is 5 plus 7 bigger than 3? No, it's not. This doesn't work. So if I had side lengths of 5 and 7 and 13, they will not form a triangle. Okay? 13's too big. If the number had been 11, I'd be good to go. 5, 7, 11, I'd have a triangle. Now, I don't know what kind of triangle it is. Obtuse, right? Whatever, it doesn't matter, but it would be a triangle. This one is not. They cannot be the sides of a triangle. If I try the next one, 5 and 8, are they greater than 13? No, they're equal. So again, if I tried to create a triangle, it would sort of collapse in on itself and it would just still be the same line segment. So this one doesn't work either. I don't have another example, but if I did and I did, like I told you, 5, 8, and 11, this one would work, right? 5 plus 8 greater than 11, the answer would be yes. So it can fail because it's smaller, like on the first bullet point, or it can fail because they're actually equal. Or it can pass. I mean, it can pass the criteria because it actually works out to be greater. Any questions on that one? Let's talk about perimeter. The perimeter of a simple closed curve is the length of the curve. Now, most of what we do is not going to actually be curves in the sense that it is curved, right? We've seen that word curve before. It's a very loosely defined word. It just means that it connects 2 points together in some way. That doesn't, and the fact that it's simple means it doesn't cross over itself. So we don't have this going on, right? This is a no-no. Closed means that it has to start and end at the same spot. So this image is something we could take a perimeter of. It's like a pothole or something. It's an egg. This image is something we could take the perimeter of. Simple, and it's closed. And it's the length of the curve. If we measured all of those pieces, or the full piece around, or whatever you're describing it as, the perimeter of a polygon specifically would be the sum of the side lengths, or the distance around the polygon. What you can imagine is taking a string and laying the string down along the edges of the shape, and then unraveling the string and measuring it from end to end. That's what perimeter is. It is a linear measurement because it's a distance, but it stretches around an object. So the first one we're going to do is a triangle. What's the perimeter of this triangle? Yeah, it is. And we get that, like we said, by summing or adding up all of the side lengths. That is 30 here. And our unit is in centimeters. It is a linear measurement, centimeters. So when we're working with polygons, we're just adding up the lengths of the individual sides. When we're working with circles, it's a little different because there aren't sides to individually measure. So on a circle, perimeter has a special name. It's still perimeter, but its special name is circumference. So circumference is the perimeter of a circle, and we call it C for circumference. The radius of a circle is the distance from the center of the circle to the circle's edge. We denote that R. So here is, it's in this fun blue color. There's my radius R. The circumference on the outside is the distance around, right? Perimeter, right? C. Diameter goes clear from one side of the circle to the other side of the circle. It's the red one that's denoted there. And it has to go through the center. That's really important. And we denote diameter with the letter D. Notice the diameter is twice the radius because the radius right here is R, and right here is R, and R plus R is 2R. The Greek letter pi is actually the ratio of the circumference to the diameter. So this, I'll bring the book next time, the one I was just talking to you about, because it actually shows this. What pi really is, like it says, is it's the ratio of the circumference to the diameter. If you divide the circumference of any circle by the diameter of that same circle, you always get this number, 3.141592 ... You always get it. It's very interesting. Every circle. We don't usually think about it like this. We usually think about it in these forms. Either the circumference equals pi times the diameter, or the circumference equals 2 pi times r. Those are the forms that we tend to think of that relationship in. It's the same relationship, it's just thought of in a different fashion. Okay, let me identify arc length, and then we'll pause for today and we'll do our examples for this next time. Arc length is actually a portion of the circle. The central angle, so imagine having a piece of pizza or something right here. This is my angle here in the middle is theta. That's called a central angle. It's an angle whose vertex is at the center. It does have to hit the center of the circle. And its sides are the radius. So here's the radius here, and here's the radius here. So that's called the central angle, that theta in the middle there. And then the arc length that's in red on the outside here can be found by taking, I'm actually going to write it a little bit differently first, the circumference divided by 360. So the circumference is the distance around the circle, right? And 360 is the angle measure all the way around the circle. If you went all the way around, you spin all the way around the circle, you've spun 360 degrees. So circumference is 2 pi r, right? And then your 360 is down here. And then if you'll notice, what happens is that you have this simplified to pi r over 180. So that is where this pi r over 180 are coming from. They're coming from that relationship. The difference between that and what I just described is that this is the circumference. I mean, the circumference means that I'm going all the way around, right? But I'm only trying to go around a measure of theta. So if I multiply that ratio by theta, then I'm actually able to find the corresponding length of the arc. Right? So imagine finding the length of the crust of the piece of pizza instead of the angle measure of the piece of pizza on the inside. But there's a direct relationship, of course, between the two items as compared to the radius. Right? Everybody knows that a slice of small pizza is not the same as a slice of big pizza. And it's not necessarily because of the number of slices they cut it into either, right? It has to do with the radius of the pizza. That's what's going on. So we'll pick up next time with examples 8, 9, and 10, and 11, and finish off this section. We'll do group work from this section. This is not assigned. You do not have to turn this in before Monday. Just bring it with you. We'll do group work in class. It'll be due on Tuesday or on Wednesday, even if I'm not here, which I won't be, but it'll be due on Wednesday, and we will start, maybe finish 13.2. We'll see what happens.